Hello and welcome to another presentation in the LADAL Opening Webinar Series 2021. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language Technology and Data Analysis Laboratory at the School of Languages and Cultures at the University of Queensland in Australia. Before we start, I'd like to read out an Acknowledgement of Country, which we do here in Australia to show and express respect and gratitude towards the Indigenous people of Australia. So I'd like to say that we as members of the University of Queensland acknowledge the traditional owners and their custodianship of the lands on which from which we're broadcasting this webinar. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. I'd also like to say that we recognize the valuable contributions to Australian and global society. If you want to know more about LADAL and the resources we provide, please feel free to explore the LADAL website. The URL of the LADAL website is shown on the screen. You can also find information about past and upcoming presentations in the LADAL Opening Webinar Series on the subpage of the webinar series. The link is also provided. And if you want to keep up with us and what's going on at LADAL, please feel free to follow us on Twitter. And if you have any questions, recommendations, or feedback, please don't hesitate to get in touch via email. I've also some great news today, which is a bit unusual, but I'm very happy to announce an official cooperation between the Media Research Methods Lab at the Leibniz Institute for Media Research, Hans Bredow Institute, and LADAL. So these two labs, one in Hamburg, and Gregor is the co-director of it, and I and Michael have agreed to collaborate and cooperate. So I'm very happy to announce this today. So it's a little announcement in addition to the welcome speech. And just to let everyone know, it might happen that we encounter some connectivity problems. If that happens, please be patient. We are trying our best, but there's really not that much that we can do. But recording typically is a little bit better. So please be patient if there are any problems with the connection. Now, it's a real pleasure of mine to introduce today's speaker and a former colleague of mine, Gregor Wiedemann. Gregor is co-director of the Media Research Methods Lab at the Leibniz Institute for Media Research, Hans Bredow Institute. His current work focuses on the development of methods and applications of natural language processing and text mining for empirical research, for example, for detecting hate and counter-speech in social media. Regarding Gregor's background, after he studied in Leibniz and Miami, he received his doctorate from the University of Leibniz. And Gregor worked in the NLP group, the language technology group, at the University of Hamburg, where I met him. So it's a real pleasure, and I'd like to hand over the floor to Gregor.
Hello, everyone, and thank you very much for this very nice introduction. So I just go ahead and start right away with my talk. So let me share my screen. And can you see the screen? I hope so.
Yeah, it's all good. I'll let you know if anything comes up.
Great. I also like to encourage you to ask questions in between if there is something I am rushing over and you are not understanding right away, or if you just want to have more details on some aspect. I'd like to answer this, of course, at this point then, and maybe not later on, so then we can just discuss this right away. Of course, we can also discuss this after the talk, but if you want to like some detail right away, just don't hesitate to ask. Okay, I will introduce you to my talk today about text classification for automatic detection of social science concepts. And to be a bit more precise here is that I have prepared examples from my work where I used supervised machine learning or text classification to identify political claims in party manifestos, to identify hate or counter speech in social media for some media research project. And then I will also present a little bit of information from a work in progress, which is about the automatic extraction of protest events from news media coverage. So let me, yeah, okay. Go forward one slide. Okay, so as I mentioned, this is kind of sample from different works. So I have two publications, one from 2019 and one from 2020, which is the basis for this talk. And in the third part, as I mentioned, I will show you some work in progress, which I have made together with Sebastian Hauns from the University of Bremen. The second part of the talk about hate speech and counter speech is a joint work together with Cornelia Fedke, also from Hamburg University. So just as a kind of overall picture for the use of text mining and computer-assisted technologies in the social sciences, I have here prepared kind of screenshots from some statistics you can find on the website of World of Science, this huge database for scientific literature, where you can do research for certain academic topics and keywords in a huge number of publications, such as scientific journals. And as we can see here, if we do some lookup, for instance, for terms such as text mining, and look at their results, we can identify steady progress in publications, or a steady increase in publications over the last 10 years, which have related or mentioned text mining in some way. And the same is also true, or something similar is true for topic modeling, although you can see here the technique of topic modeling somewhat was used in 2016 to 18, much less than it has been used since 2019. So there has been a huge boost actually in publications which use topic modeling as one major method to explore large collections of texts. So those two, text mining and topic modeling, can be seen as kind of unsupervised methods of machine learning, or unsupervised methods of text analysis. So you investigate texts without lots of prior knowledge. And in contrast to that, we have more deductive approaches in social sciences, where we actually have predefined categories in mind, which we want to analyze in large text collections. And usually there are methods, computer-assisted methods, combined in a way that is referred to as automatic content analysis in the field of media research and communication research. And in the field of computer science, you usually refer to text classification or supervised learning for this task, where you have predefined categories. And also here we can see that there is some sudden increase last year in the use of automatic content analysis methods, although it has been, the term itself has been used kind of steadily over the past 10 years. And we can see that this automatic content analysis is in rather lower numbers compared to text classification or supervised learning publications, which use these terms and have been used quite a lot more over the past decade. So this is just to give you a short impression that we are dealing here with a field of growing interest, and which is really a fresh and new development in parts, and that the major driver here is usually that there are some bigger developments in the field of computer science related to automatic text analysis, like these methods of topic modeling, or new methods of supervised classification and supervised machine learning, which then spill over to the analysis of text in the field of social science and communication science. And this is, of course, due to the fact that we are dealing with a world of big data right now. So we are confronted in these fields of applying research, such as social sciences, with the fact that we have tons of texts which we cannot analyze or read any longer for social science purposes manually or by hand, and it's also not feasible to code larger samples of those texts by hand to investigate all the questions which are related, for instance, to the publication of online material and in online newspapers or in social media and so on. So the natural approach, of course, here to deal with this new world of big data is that we use automatic coding for content analysis, and this automatic coding somehow relies in a more simple way on simply observing dictionary terms, but nowadays, as a spillover, as I mentioned, from computer science, we more and more rely on methods of machine learning to automatically categorize texts. There's been also a famous publication by Hopkins and King in 2010 about specific social science goals for content analysis, or for specific social science goals for text classification. And they observe here that the goal often is that we want to know about certain proportions of categories in text collections instead of having very correct individual classifications of text. So the idea here is that we want to know about the share of a certain category in a data subset, for instance, to perform cross-sectional analysis, or we want to identify trends. This is the relative change of proportions between data subsets, for instance, to conduct time series analysis. And this might be a major difference to the way how text classification is usually perceived and evaluated in computer science, where we want to have a very precise individual decision. So the individual decision, for instance, would be, as an example, which everybody of you knows, is your spam filter in your email inbox. And your spam filter, of course, needs to decide very accurately for each individual email, is this a very important email which I should keep, or is this a spam email which I should rather delete or hide from the user? And wrong decision in that email classification could be, of course, of severe consequences if you miss a very important email due to a wrongly classified email. But as Hopkins and King point out, social sciences are not interested in these individual decisions, but want to know about what is the share of false or spam emails among all emails, for instance. So as I mentioned already a little bit, is that we usually distinguish two specific types of machine learning. One is unsupervised learning, also known as clustering. So here we want to identify structures in the data set, for instance, groups of similar data points from the pattern in the data itself. And in contrast to unsupervised learning, we have methods of supervised learning, also known as classification. And here the task is to sort data points into predefined categories. And the sorting or this categorization is done by a machine which is trained on human labeled data. So human is in brackets here because, of course, these labels could also stem from other processes. But usually in social sciences, for instance, we have labels which we attach, or categories which we attach to texts as training data, and then from these labeled data an algorithm is trained to re-identify these categories in unseen texts. I also repeat a little bit to introduce you again to the method of content analysis and manual content analysis, especially to make clear what are the different steps here if we switch from a manual process to some automatic coding process, and also what are the benefits here. So usually in manual coding for social sciences, for instance, for content analysis, we have a base population of texts, and we just draw a sample from this base population, which we then have, which should be, of course, a kind of random sample that it guarantees that it somehow replicates the characteristics of the space population. And then we have our codebook definition, and we start a manual annotation process of this sample of text. And usually, to ensure the quality of our coding, we measure something which is called the intercoder reliability. So different persons are asked to apply this codebook to the text and to categorize or label these texts. And if we measure a high reliability between the labels of different coders, we can be happy and go on for the final program of coding of the entire sample. If we cannot achieve a high intercoder reliability, we usually have to redefine categories in our codebook, or we have to refine the examples given, or we have to re-instruct the coders how to do their job better, just to make sure that we can reliably identify those categories in the text. In the end, what we have is a final coding of the entire sample, and then we can do some aggregate results or perform some analysis based on aggregate results. For instance, we can identify the share of certain categories. Here are some example categories mentioned, the share of these categories in the entire sample. What is now changing if we switch to a computer-assisted workflow which employs supervised learning? We just have a couple of new steps in here. So we start again with our base population and draw a sample, apply the codebook, and perform the manual annotation. So this is more or less similar to the manual process. But as soon as we have a reliably annotated sample of texts, which we can use as training data, we now start the machine learning process, which first conducts a step of feature extraction and feature selection. So we look for specific, or the machine looks for specific characteristics in the data to distinguish between the different categories. And based on these features, an automatic classification algorithm is trained. There are a lot of different algorithms out there which achieve different performances and which should be selected according to the task. And of course, here we have a new process which needs to, where we need to, sorry, my slides slipped here a bit. Okay, yeah, of course, we have a new process here where we need to evaluate the performance of this machine learning approach in addition to the performance of the human labeling approach. So we do that usually by applying some performance metric, which measures the agreement of the automatically generated labels to the human labels, which we have coded earlier. So usually we have a test set, which is split from the training data and which is held out and not used for training the algorithm. And then we can just, for the quality performance metric, we can compare what the algorithm thinks text belongs to and what the human coder has annotated. And if we have a large agreement here, we can also make sure that the algorithm is doing its job sufficiently well. And what we achieve here in the end is, and what is the big advantage compared to the earlier approach, is that we can now apply this automatic algorithm-based coding not only onto the sample, but onto the entire base population. If we have a valid classifier, we can easily and cheaply classify hundreds of thousands or millions and billions of texts. And that can, of course, open up for much more exciting analysis. For instance, we can filter or facet the space population data in any imaginable way to make comparable analysis. So we just do not only receive a number of shares on this certain base population or the sample of the base population, but we can actually compare, for instance, different time frames and conduct these time series analysis, or we can conduct comparisons among different authors, publications, and so on. So this is a huge advantage over the non-computational approach, and it of course makes sense to go further into this direction these days, where we have the machines and the algorithms available to perform the classification with sufficient quality for our projects. So I will introduce you to two lessons from three different computational social science projects I have conducted. The first thing is that we can learn how supervised machine learning can contribute to automatic content analysis via active learning. So active learning is one specific way of performing machine learning and supervised machine learning. Then I will introduce you to some application of deep learning with a specific type of neural networks, so-called convolutional neural networks. And the third example I just briefly will introduce is the idea of transfer learning with bidirectional transformers, which is the most recent and revolutionizing technology in this field. So let's start with the first example. So these images here always illustrate a little bit where we are in the talk, and they are meant to illustrate the topic I'm talking about. So here we start with active learning for coding of party manifestos with a logistic regression classifier. So what is the goal here? There is in political science a huge project collecting party manifestos all over the world. And this is a project conducting manual content analysis on these party manifestos since the 1980s. So they have collected hundreds of thousands, not hundreds of thousands, hundreds of or thousands of party manifestos so far. And then they have a fixed code book of different policy fields and policy actions which are coded in these party manifestos, and then this allows for cross-country comparisons or comparisons over time for different, for the evolvement of the importance of different policy fields, for instance. And I have used this party manifesto data set or parts of this data set to conduct experiments of active learning to see, can we replicate the results of these manual codings with automatic machine codes. And I took from the party manifesto dataset 42 manifestos of English-speaking countries from the US, UK, Ireland, and Australia. They altogether contain around about 44,000 sentences. And then I took the 10 most frequent categories. All in all, there are more than 50 categories in the dataset, but I took the 10 most frequent ones and used a simulation of active learning to test this scenario if we can replicate this huge effort of manual coding with much less effort of computational coding in a supervised way using active learning. So to give you an example from this data set is we have this very short sentence in the party manifesto of the US Democrats from 2012, which says, "We will strengthen Medicaid," and this is put into the category of welfare state expansion. And like this, we have the other 44,000 sentences, and we'll try to label them automatically based on smaller parts of training data from this data set. So as a background, I mentioned already that we have to represent our texts for the computer by its features. And usually the logistic regression classifier or support vector machines, which are also very frequently used, they rely on a feature representation of text, which is the so-called vector space model. The vector space model just abstracts from the natural language text in a way that we represent now a document as a vector. This is done in a way that we first identify the vocabulary of an entire collection. So that is the set of all unique words which appear in all the party manifestos of my data set. And this vocabulary can be very huge. Usually it can be in this example of more than 500,000 different unique words, for instance. Of course, it is hard for the machine to deal with such a large vocabulary. So usually it is reduced to the most frequent terms. For instance, let's say all terms which occur at least 5 or 10 times in the entire data set, and then we end up in something in the range of 10,000 different word forms. So our vector then contains 10,000 cells, and for each of the cells we can put a word frequency value into that cell. For instance, we have here the word Europe, and say the document 1 contains the word Europe 1 time, or since we have representation not of documents but of sentences, the word welfare, for instance, is mentioned twice in the second sentence or something like that. So in the end, our documents are these 10,000 elements long vectors, and our corpuses are represented, or corpora are represented as matrices, where we have the number of documents as rows and the length of the vocabulary as columns. So we receive very large data objects where we can perform statistical analysis on and perform some data mining operations on. And the advantage, of course, here of this vector space model is that we have a very efficient data structure to encode the semantics of documents or sentences in these vectors. But we lose, of course, lots of information through this back of words approach. So we do not have, for instance, the information about the sequentiality of the words, which words have appeared in which order in the sentence. And I mentioned also we throw away lots of the vocabulary to make these data objects fit into the memory of a computer, for instance, and not to put every occurring word into that data object. And of course, this leads to loss of information for the entire automatic process as well. So how about active learning now? The idea of active learning is that we interact with the computer and the human coder in a alternating way. So Burr Settles describes it in a review paper 2010 with the words, if the learning algorithm is allowed to choose the data from which it learns, it will perform better with less training. So the idea here is that we do not randomly split a training set or sample a training set from a large data set and just label this random training set, but instead we start with a very small sample with which is sampled in the beginning, for instance, randomly, and then perform the manual annotation as before to receive a certain intermediate training set, train our classifier based on this very small beginning training set, perform the automatic classification, but not only of this training set, of course, but of the entire base population, and receive preliminary codes from for labels, not for labels, for each data point in our base population. And then we have some stopping criterion to be defined. And if the stopping criterion is fulfilled, we can perform the final analysis. But usually in the beginning, of course, the stopping criterion will not be fulfilled, and we perform another step of sampling new data points, unlabeled data points from the base population, and then enrich our training set with new manual codes, perform again this whole training and classification step, now with the improved classifier, since it has seen more training examples, and we receive an updated set of preliminary codes, and in the end can again decide whether our classification quality is now sufficient or not. And we will repeat this step over and over again, maybe up to 100 times if we sample only a small number of examples each time, until we actually finally achieve sufficient quality of the process to decide now we are happy with our classifier performance, and we can go to the last step of taking these preliminary codes as final codes and do the aggregated result analysis. There was one question in the chat. Can you say something about why the algorithm does better with less training, maybe too much training over the search space? So the question is about why we think it will be better. So this is the secret lies now here in the entire sampling process. So the algorithm on some or with a certain strategy is now able to decide which data points it wants to look at. So we can use different strategies. I will talk about that a little bit later. But the basic idea is that, or the most basic idea is that the classifier, the classification algorithm produces an output of probability for each label. And there are labels where it is very certain that it took a correct decision. So these examples will receive a probability of about 1 for receiving a positive label, for instance, or a probability about 0 for a negative label in another case. And then we have examples where the classifier is not so sure because it has not enough information. And these examples will receive a label probability of around 0.5 or 50% chance of getting the one label or the other. And if we now show for the next round data, manually annotated data to the classifier, which has been selected around this decision boundary, then it of course gains the most information from these examples instead of presenting, for instance, just another random sample of training examples. So the idea here is to provide the most informative, to provide the data points with most informative labels to the classifier. Yeah, so I did some experiments with this setup. So I, of course, first performed a conventional classification setup as a kind of baseline where I just have a larger training set and test set split. So in this case, this was half-half. Half the data I took for training and half the data for test to see what is the more or less upper bound of performance we can achieve with the standard setup and with a very large training set. And then we can compare this to different active learning scenarios. So we simulate this active learning of repeated labeling by annotators for unlabeled data sets or unlabeled parts of the data set. And we have the random strategy of initial base, and we can distinguish between different starts of the process, of course, as well. So we have the random initial training set sample, which should be the optimal case. But of course, we can also imagine that if we have, for instance, continuous stream of data, then we have actually biased initial training sets. So if we are sampling our data right now for social media data, for instance, but we want to apply our training set to classify social media posts for next month, then this is a kind of biased training set, since the data we are collecting today will have different feature representations and distributions than the data we will receive next month. And so this is something we can test here in the setup. How is active learning actually able to somehow smooth the negative effects of biased initial training sets? How do we evaluate the whole process? We, of course, also keep our holdout test set. There we use the same test set as also for the conventional classification setup, so that we can actually compare the performances. And we measure, since Hopkins and King have pointed out that we are interested in different measures rather than individual classification performance. We measure our performance here based on the ability to predict proportions of categories in the dataset correctly, and we do this by root mean square deviation. And we also measure the ability of how to predict trends correctly in the data by Pearson's R correlations. The questions we want to answer is which strategy of selecting new samples from unlabeled data accounts best for biases in initial training sets? When do we stop the learning process, and how reliable is the process in the end? So I use here a classification algorithm called logistic regression with two regularization. The hyperparameter tuning is done by a 5-fold cross-validation. And we have, as I mentioned already, 50% of the data as a holdout set for our tests to test the performance in the end. Then this feature extraction process also just does not take only the single words, but we perform so-called stemming operation. The stemming operation is just cutting ends of words to unify the vocabulary and to compress the vocabulary even further, to make it more informative for the classifier. Then we also concatenate two consecutive words to additional bigram features here. So this somehow is a little bit helpful to prevent this negative effect from the back of words approach. So we are able to have at least the sequence of two words, of two consecutive words in our documents as features in the data, and we also add additional bigrams where we remove stop words in between, so that we have a little bit more informative features with not relying on stop words such as articles and so on in the data. So this these features which are going into the entire process here are the basis for the classifier to train a model and then predict these 22,000 unlabeled sentences. And we can now see that we use the first evaluation set up with the standard training and test scenario where we have half of the data as training, that we can actually predict for the entire data set and for single manifestos with very high accuracy these shares of the 10 different categories. So for the entire data set, our root mean square deviation is somewhat between 1 and 2% of error, where we just can predict the actual category share with only an error of 1 or 2%. And for the single manifestos, this is also for all the different 10 categories, somewhat between 1 and 3% more or less. So for single manifestos on each single manifesto level, this is a little bit less accurate, but for the entire data set, it is quite accurate. And even 2 to 3% for single manifestos can be considered actually as very comparable to the performance of human labeling. Of course, what you can achieve maybe there. For the trend prediction, this is also rather high. So we achieve Pearson's R correlations between observed actual true trends in the data and predicted trends in the test data of around about 0.5 to 0.9 for the individual categories. So we can actually say machine learning in total or supervised text classification can solve these two tasks of trend prediction and category share prediction with sufficient quality. So the question now is, if we do not want to label 22,000 data points as training data, can we be much faster and use much less training data with a kind of active learning strategy? And we compare here 3 different strategies of active learning. So this repeated process of sampling new data points from the unlabeled data, label them and integrate them into the training set for retraining the classifier. And in our experiment, we for each round, we sampled 2 to 10 new examples. So you have here in these graphs the number of iterations, and 20 means here that we have 20 times sampled 10 new examples from the unlabeled data, labeled them, and trained the classifier on to perform this classification and evaluate the trend prediction target or the category share prediction target. And you can see that for all the compared strategies, we have a steady growth in the performance over the iterations and achieve here Pearson's R correlations, which are even above the baseline, which I presented on the earlier slide, that we have here overall categories aggregated an average of more than 0.9 Pearson's R correlation, or 90% of this values range. We compare actually random sampling of data from the unlabeled set to this strategy I already mentioned, which is called the least certainty strategy. So all data points which are predicted at one step of the time, one time step with a label probability of around 0.5 or 50% chance, like random coin flip guess, which label to choose. And if you choose this strategy, this is called least certainty. But of course, you can imagine if you just stick to this strategy in a very imbalanced data set, such as we have here. So we have the 10 categories, and each category only makes up for somewhat between 2 and 10% of the entire data set. There is a higher chance that we actually sample uninformative or negative data points which do not fit into a certain category if we choose this least certainty strategy, because this data set is so imbalanced. And we can, for this, introduce a bias correction such that we actually tend to select rather more potentially potential examples which fit into a certain category which we want to investigate. And we actually measure the imbalance of these categories in our currently selected training data and try to select more of those examples which are not just around the 0.5 decision boundary, but which are more on this side of the boundary, which we have less represented in our current distribution of the training data. And this bias correction, which is a specific formula, which I just omitted here on the slide, but this bias correction actually improves the least certainty strategy of active learning quite a bit, and leads, at least in the beginning, to much better results in the trend prediction than the least certainty strategy. So in the end, both strategies somehow approach each other and are not really producing very distinguishable results any longer, but both active learning strategies compared to the random sampling strategy are performing much, much better. And this is also true for all the other evaluation metrics we can see here. And we can see that we achieve a rather sufficient performance, maybe around about 100 iterations where we approach the 0.9 line here with already 400 to 500 positive training examples. And we have seen much less or have to have labeled much less training data to achieve this compared to this standard setup of random training and test set sampling. Second question now was, when do we know to stop this operation? And the answer basically is here when we observe that the classifier is not learning so much new things from seeing new examples. And we can actually try to infer or to have a heuristic when this is the case. And we use the predicted labels on the entire unlabeled data set for this. So the idea basically is here we have our large unlabeled data set, and at each step in time, we predict with the current state of the classifier labels for these unlabeled data points. And we can now compare how are my my currently predicted labels, how do they compare to the labels from the previous learning step. And if the labels do not switch very much, or if they are more or less the same labels predicted than in the step before, we can actually infer that the classifier did not learn anything new from the last 10 examples it has been presented with. And if that happens a number of times in a row, we can actually be quite sure that the most informative examples for the classifier to actually make a decision have been already collected from the unlabeled data set. And this is the time where we then can stop the whole process. And this is called a stability measure. So the percentage of same predictions on the unlabeled data set between consecutive active learning iterations. And we stop the whole process if 99% of the labels do not change 3 times in a row. And if we just interrupt the whole process at this point in time, for instance, for these 10 different categories, we end up at different points in time or at different steps of iterations. So the category 506, one of the largest actually in the data set, is stopping already after 70 iterations. So the language variation in this category is not so high that we need a lot more examples here. Only a few number of examples which are actively chosen by the classifier are already enough. And for the category 504, we actually need almost twice as much iterations until this stopping criterion is reached. So here now is the comparison to our biased initial sets as well. This is interesting to see if we have a biased initial set, for instance, where we start with a bias of certain time frames, for instance, party manifestos, which have been published before the year 2000, and apply this to the set of party manifestos published after the year 2000. Or we have left-leaning parties versus right-leaning parties here, and we have Australia and the US in one part of the initial training set, and we apply the data then try to learn also for Ireland and the UK. Then we see that the active learning scenario actually after some time also is able to correct for these initial biases. So some categories do perform worse in the beginning, but actually all of the learning progress curves here end up in more or less similar regions, like the random initial training set scenario. Even here for this bias of time for the category 301, in the end, we end up in kind of similar region of the quality metric, like for the random sample scenario. So the active learning scenario can still be useful to produce valid results, even if we start from a very biased training set. And of course, to make this evaluation not for a single run, but to see how reliably it works if we perform this process, which involves a lot of random selection of data points for the initial training set generation. Of course, we have to repeat this, and here you see the results for 100 repetitions of this experiment, and we can see that we somehow reliably have a rather narrow band here of for each of the categories, where we end up after this active learning simulation, where the stopping of the whole process is roundabout, for all the categories, stops roundabout after 100 iterations for the 5 largest categories, and for the 5 less frequent categories in the dataset, we have a larger distribution here. So some of the categories are stopping much earlier and some much later. And this is also consistent if we have this selection of initial training sets with a huge bias in the data. Still, this does not affect the outcome of the process very much. So the last question then was, how reliable is this process in total? And also for the 100 repeated runs of this experiment, we can see that we can be quite sure to end up in this region about 0.9 Pearson's correlation for the predicted categories compared to the true categories of the data in the entire data set. And the initial bias, with the exception for this category, does not drastically lower the entire performance of this whole process. So the lessons learned, to summarize, is that the social science specific goal of proportional classification and trend prediction must account for uneven feature distributions in subsets of the text collection, and active learning is able to correct for those biases in initial training sets and allows for cost-efficient, reliable, and valid proportion and trend prediction. Moderate individual text classification performance in terms of F1 scores or kappa evaluation is also already enough to predict proportions and trends with high accuracy in the data. So this is maybe also a very important lesson here, that the evaluation metrics we achieve here with regard to the standard metrics used in computer science, for instance, or in intercoder reliability, they are rather low. So we have here values around 0.5 only, which are usually not considered as sufficient for manual content analysis or in an NLP scenario. But if we switch to the proportion and trend prediction evaluation metric, we see that even with these rather moderate performance results in terms of individual classification, we can actually correctly identify the trends and proportions in the data. So two shorter examples I want to introduce you to are then deep learning and transfer learning. So the deep learning scenario for automatic coding are used to identify patterns of hate speech and counter speech in German Facebook user comments. And here we have a data set of 360,000 user comments written under 2,900 posts on German Facebook pages from media outlets in 2017. And we want to know about the distribution and the dynamics of hate speech and counter speech in this segmented publics of social media. So one of the questions is, for instance, which topics and strategies are hate and counter speech mostly associated with. And here we combine different methods of automatic content analysis. So for instance, LDA topic modeling, which I will not explain here further. But one part is text classification, and then we also use co-occurrence analysis to find patterns of co-occurring topics and text classes. But the major component I want to speak about today here is this text classification component, where we have a classifier distinguishing user comment into either hate speech, counter speech, or neutral comments. So deep learning is actually a kind of catch term referring to neural networks with one or more hidden layers in it. So in a neural network, usually we have some input representation, for instance, a sequence of words, and then there are hidden layers which compute certain intermediate values from these inputs, and these hidden layers can represent kind of latent features, and these latent features in the end are used to produce an output decision, for instance, in a binary classification decision, something like 0 or 1 for a specific label, or in our case, we actually do not have a binary, but a ternary output decision for this hate speech, counter speech or neutral comments class. And typical deep learning architectures are so-called convolutional neural networks, which actually have been developed for image classification first, but they have been applied to text successfully too. And then there are long short-term memory networks, which actually are a kind of recurrent neural network architecture. And those recurrent neural networks are useful to classify time series data, which text can also be considered as. So you have the sequence of words in a sentence or in a document, and that can be also considered as discrete time series data, which is successfully to be classified with these LSTM networks. So the major advantage compared to the vector space feature approach I presented earlier here is that we feed entire text sequences now into these deep learning networks instead of these back-of-word vectors, which we had earlier, which had no information about word sequence in it. So here's another figure from this convolutional neural network papers for sentence or text classification from 2014. And we now, as I said, have the representation of the entire text sequence here. For instance, the sentence "wait for the video and don't rent it," which is from a sentiment classification data set. And this now represents each word as an embedding vector. So the word meaning actually is represented as a kind of embedding vector, and we can now, with these convolution operations, combine the different embedding vectors to intermediate values again, and to produce these output values. And the convolution architecture actually combines pairs of words or triples of words or sequences of a certain number of words, like two bigrams, trigrams, and so on in the vector space model. But here we can have actually larger n-grams to combine easily. And we combine not only the words, but actually their semantic representations as embedding vectors, which makes this model much more efficient to represent actual sentence semantics. Our training data from our large data set is 17,000 comments roundabout. They have been coded with Krippendorf alpha intercoder reliability of 65%. And this makes up in the end for 4,000 hate speech comments, around about 4,000 counter speech comments, and 9,000 neutral comments. We use a combination actually of these recurrent and convolutional networks with 3 different filter sizes, and we use pre-trained fast text embeddings for this entire classification. So this is also a major advantage compared to the document term matrix approach or the vector space approach, that we actually have a possibility to represent word semantics from pre-trained data, and can put much more information into the classification process, for instance, about the similarity of certain words, which do not then have to be part of the training data to be able to be predicted correctly. And since hate and counter speech detection is quite hard task, since these categories are a little bit hard to be defined, especially in a social science conceptualization way, where you do not only look for toxic or foul language, but you want to actually have also represented the discriminatory aspect here. So our overall performance evaluations are not overly high. We achieve 71% accuracy or F value of 66.9 So this is okayish, but actually not super high. But as we have seen from the previous examples or experiments, that might still be enough to represent or to predict categories and trends in the data correctly. And this is what we want to achieve here in the end. So I mentioned already we have LDA topic modeling and can receive primary thematic labels from this process. And we have our hate and counter speech labels from the supervised text classification approach. And this we have now for all the 360,000 comments in our data set. And we can investigate the thread structure of user comments and specific patterns of topics and classes in this thread structure. And this allows us, for instance, to identify for each of the topics in our data set, which I just omitted how we achieve how we get those topics, but we can now actually measure the amount of hate speech or the amount of counter speech in these specific topics, for instance. And we can see here that our topics, political parties or refugees and migration, and those are the topics with the most or the highest share of hate speech in our data set. And we have a lot of topics here in the bottom, which are more specific to the text form of user discussions, which are related either much more related to counter speech instead of hate speech. For instance, the discussion about which information is considered as facts or fakes, or something like humor and irony. This is much less connected to hate speech than those topics here above. So to give you an example, we have a user comment. You can also set a whole country on fire, like Merkel's Grand Coalition, ethical politics as it could not be worse. This has been labeled by our classifier as a part of hate speech, and has been assigned with the topic hate against Merkel and the government. And this is the data we can now use for our social science research questions to further investigate, for instance, to identify typical patterns of hate speech co-occurring with hate speech, or hate speech co-occurring with certain patterns of counter speech. And for instance, we can find in our data set that hate speech, which is directly addressed against the government or Angela Merkel as the Chancellor of Germany, this is usually countered or associated with counter speech referring to the right-wing political party and its party manifesto, or the right-wing party and the its relation to democracy. And we also find a large share of simple insults as a specific form of user discussion text as a counter speech part to this specific hate speech category. So this is a very interesting thing where we can, or to sum up here, what we can learn from this research is that text classification via deep learning actually improves, or is able to improve the classification results for complex categories. So hate speech and counter speech are rather context dependent here, and very sorry, I have to put in the power plug in my computer. Okay. Yeah. Hate speech and counter speech are very context dependent, and for this reason are not so easy to identify in the data. And the new deep learning methods actually represent the complexity of natural language much better. For instance, the sequentiality of natural language. And we can make use of word semantics from pre-trained embeddings. And this allows us to also identify these more complex categories with sufficient quality in the data set in an automatic way. And we again have seen that moderately accurate text classification can still give valid insights into typical discourse patterns. For instance, here this co-occurrence of specific thematic topics and hate and counter speech classes in the data set. And this can be observed via standard methods of co-occurrence measuring or data mining methods, where we just operate on these labels and class labels and topic labels to find typical patterns in the data. So this can give us much better insights into these large data sets than just having a look at qualitatively at small samples or just the typical way of performing text mining like key term extraction or something like LDA topic modeling, which alone would not be able to identify these hate speech and counter speech patterns itself. Last quick example will be the BERT classification with so transfer learning with bidirectional transformers, and I use this currently in a protest event extraction project where we have news data from 4 local newspapers in Germany, and we want to know from 50,000 articles in those 4 local newspapers which have been published over the past 20 years. How many protests initiated by whom, about which topic, and with how many attendees are covered by these local media outlets. So here again, we have text sequence classification, so the entire newspaper document, and we use, instead of the aforementioned CNN by LSTM networks, we use now a new technology which has been first published in 2018, and the official paper came out only 2019. By a team of Google, and they have published the so-called BERT language model, which is short for bidirectional encoder with recurrent transformers. And these transformer architectures are actually a huge revolution in natural language processing these days, because they outperform by large all previous approaches and are very flexible to be used in different setups. And most amazingly, they can be pre-trained on very large data sets in a way that we can reuse and transfer the knowledge which has been contained in these pre-training data sets to fulfill a new task much better. So again, here, this is basically a method to reduce the amount of training data for our actual task we want to perform, and can make use of much more large unlabeled data sets from other contexts to improve our actual task. So the actual task here is, as I mentioned, the sequence learning. We have annotated newspaper articles, which is here starting with the headline, Bremen, Protest der neuen Rechten, so protest of the new right in the city of Bremen. And then the article starts and has been labeled with lots of different categories, such as protest event 1, and then there is the protest event title, and the protest event topic, like it is directed against Muslims and Islam. And there are lots of different variables which have been coded in the text. And the task now is for this BERT model to apply actually automatically these labels to unlabeled documents. And this is a quick introduction how this model is actually built and pre-trained. So it contains different levels, like for instance, these embedding levels, which we already had in the LSTM CNN model, which contains certain word semantics or token semantics here. And then in addition, it also has these positional embeddings where word order is, and the relation between words in a sentence is specifically encoded, which improves the entire model here. And the very creative and innovative pre-training idea is actually that it is trained as a so-called masked language model. So it is actually pre-trained by billions of texts from the entire internet, and in a way that it is presented with a sentence where certain words are just missing. And the model is now pre-trained in a way that it needs to guess what words are actually in these missing masked parts here. So the input sentence, my dog is cute. Separator, next sentence, he likes playing. And we have a masking of the word dog and the word likes, and the model is now asked to guess which word to fill the gap. And then it can be, of course, make a guess and be corrected with the correct value, which should be there. And by this correction process of teaching the model how to fill in these gaps, it encodes not only certain word semantics, but actually the very much of context semantics and sentence semantics in its entire architecture. And these semantics, which are then in the model weights are encoded, they are surprisingly useful for lots of different NLP tasks, such as text classification, sequence tagging, but also question answering, where you, for instance, want to find an answer in a text to a given question. So this architecture is actually super successful in NLP and starting a kind of revolution by just outperforming all previous approaches on how to perform natural language processing. And we can actually, as I said, it can be pre-trained on billions of sentences. And what also is amazing here is that it has a built-in disambiguation of words through its bidirectional contextualization of word embeddings. So since it is presented with the entire sentence at once, you can actually have the contents of left and right to each word, the context, and so each word, even if it's the same word, has then a different contextualized embedding representation here. And this allows for this internal disambiguation. So ambiguous words which have different meanings, polysemous words, are actually represented as different semantic entities within this model, which makes it so successful. So for instance, to give you an impression, we have a sentence like, for the 28th time, Legida, which is a specific protest group demonstrated in Leipzig on Monday. And we can identify now that the word demonstrated has in the internal representation of the model the meaning of a protest event, while if we have the sentence, the finance senator demonstrated the city's e-government app on Monday, the word demonstrated is not associated to a protest event. And since in its embedding space, it is located in a much different region. So even if it's the same word, the different word meanings are associated with different semantic regions in the entire embedding space of the model. Same for numbers, for instance. So from the context, we can now infer that this number here is the context of the number of participants of a protest event, while this number here is not relevant for the number of participants, since it only refers to the number of police officers which secured the protest. So lessons learned here is I cannot present too much yet, but we can at the moment already say that our preliminary results show that we, for the relevancy classification to decide whether a certain report is actually reporting about a protest event or not, this works sufficiently well with an accuracy of 93% or more, and only on a training set of 500 relevant articles already. So there is still some space for improvement, but we are quite happy already with this first preliminary results. And in total, to sum up, transfer learning with transformers may be also a major breakthrough for automatic content analysis in total, since we can just account for the characteristic of text that it is formulated in a sequence, and the sequence actually makes up for its semantic meaning as well. We have our built-in representation of polysemous and synonymous semantics by these contextualized word embeddings, and we can allow for classification on different semantic levels, such as word level, sentence level, or documents, which is quite interesting for lots of computational social science tasks. So to sum up the entire talk, we have seen about or learned about active learning, how to combine human and machine intelligence during coding to improve automatic coding. We have learned about deep learning, how actually neural networks help us to better cover natural language aspects. And then we have seen in this last example the idea of transfer learning, where we pre-train a neural network on super large unlabeled data to improve our coding for the actual target task. And this is done this is achieved in a way that these pre-trained models somehow encode common sense knowledge from these unlabeled texts, which is helpful to fulfill the actual task. So all in all, we can reduce the amount of manual coding to perform content analysis with these approaches, but still 500 or labeling 500 newspaper articles, for instance, for a project is a tedious task. So even if we have a lot of improvement here in this direction, still supervised text classification and automatic coding is not something which can be done by just pressing a button or labeling only a handful of comments. We still need to perform a lot of manual work to achieve sufficient results. Although the categories can become complexer now, and the semantics we can capture can be complexer, we still have to keep in mind that we have to put a lot of effort into these projects. So thanks for your attention. I hope you enjoyed learning from these 3 examples, and I'm happy to answer your questions.